Hi, my name is Fraser Robinson. On behalf of myself and my supervisor, Professor Goldie Najat, I'm here to present a deep learning human activity recognition framework for socially assistive robots to support the reablement of older adults. As adults age, activities of daily living become more challenging to complete. Reablement uses a do-with approach rather than a do-for approach to help older adults maintain activity of daily living independence and stay in their own homes for longer. Socially assistive robots have the potential to increase capacity of delivering reablement care. However, they are currently limited in their autonomy. To address the autonomy issue of socially assistive robots in home environments of older adults, we develop a multi-activity human activity recognition framework to be deployed on socially assistive robots. The novelties include the design of a vector embedding, a unique spatial mid-fusion paradigm, and also an ADL classification model that extracts both generic and specific ADL features from observed ADLs. We incorporate the unique spatial mid-fusion strategy and ADL embedding for autonomous ADL classification. This is our proposed deep learning architecture. And as you can see, it is a multimodal deep learning network that uses RGB video, 3D pose, and an RGB image, which will go into more detail of how each is processed by their respective backbones. The video backbone network architecture is based on the X3D small architecture and adds a custom ADL feature extractor to the last layer for extracting specific ADL features. It learns scene and motion features from the video that is compressed and cropped from the initial input. The pose backbone consists of 3 parallel sections at its beginning, a graphical neural network stage, as well as a self-attention and a skip. Graphical neural networks take advantage of the inherent structure of the 3D joint position human skeleton, which can be leveraged to understand the positions, while the self-attention understands joint dependencies between joints that are close and as well as those that are far away. The object detection backbone is built on the YOLO v5 architecture and outputs object locations in the 3D space of the objects. Spatial mid-fusion combines these 3 separate multimodal inputs and their features into a single unified feature map. Mid-fusion enables the learning of intermodal relationships and is also able to unify the dimensional understanding across these inputs. You could see an example of our spatial mid-fusion applied to the pose data in the bottom. And this is also done for the object locations, all relative to the initial video. The ADL embedding vector is essential for our work of understanding unseen activities and also customizing robot behavior to specific changes in user ADL differences. Essentially, it is a low-dimensional representation of any activity, and it can be seen how significant this low-dimensional representation is on the right-hand side. For training and testing, we use both the ICRA Activity 3D dataset and the Toyota Smart Home dataset with refined skeleton data. The ICRA Activity dataset, we selected only 11 ADLs from the list of 55, and this includes basic activities including eating food with a fork, washing hands, and laundry. Toyota Smart Home, on the other hand, includes both basic activities such as take pills and compound activities such as cook and clean up and cook and cut. Hyperparameters can be seen on the right-hand side for training. Experiments show that testing on ICRA, which was the first to consider real-time application, gave a test accuracy of 86%, while the Toyota Smart Home accuracy of 73.5% is comparable to cross-subject accuracies from other works. We also conducted an ablation study on the ICRA test set to understand the significance of multimodality in our model, and found that the combination of pose, RGB, video, and object significantly increased test classification accuracy compared to unimodal and even dual modal approaches. In analyzing our ADL embedding space, we were seeking to increase the separation between classes and also to clearly see and understand using t-SNE representation the various groups of ADLs in a visual manner. You can see the RGB video compared to the multimodal approach and the ADL embedding spaces that they represent, where inter-class separation is increased and there are more distinct pockets of similarly linked ADLs. Multimodal embeddings of new classes show that new ADLs can be contextualized based on the known activities, such as putting on cosmetics being similar to brushing hair, while freehand exercises is unique amongst all ADLs. In conclusion, we present the development of a novel, deep learning multimodal ADL recognition architecture, and ultimately future work will include implementation of the architecture on a physical SAR for ADL assistance. Thank you to our funding sources, and also a special thanks to co-author and supervisor Professor Goldnita Jat, as well as the members of our lab. Thank you so much.